Hello everyone, thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Properties of Reinforced Concrete, and it is going to provide you a broad overview of the material stress-strain relations and also the properties of reinforced concrete. I am going to give you an overview of what I am covering today's video. First of all, we will have a look at some fundamentals of the concrete and steel stress-strain relations. Then move on to the shrinkage, creep, and durability. Then wrap up with conclusions. The loads on a structure cause dissolution of its members with resulting stresses and strains in the concrete and the steel reinforcement. To carry out the analysis and design of a member, it is necessary to have a knowledge of the relationship between these stresses and strains. Concrete is a very variable material, having a wide range of strengths and stress-strain curves. A typical curve for concrete in compression is shown in Figure A. As the load is applied, the ratio between the stresses and strains is approximately linear at first, and the concrete behaves almost as an elastic material with virtually full recovery of displacement if the load is removed. Eventually, the curve is no longer linear and the concrete behaves more and more as a plastic material. The ultimate strain for most structural concretes tends to be a constant value of approximately 0.0035, although this is likely to reduce for concretes with cube strengths above about 60 Newton per millimeter square. Figure A is typical for short-term loading. Concrete generally increases its strength with age. This characteristic is illustrated by the graph in Figure B, which shows how the increase is rapid at first, becoming more gradual later. The precise relationship will depend upon the type of cement used. That shown is for the typical variation of an adequately cured concrete made with commonly used class 42.5 Newton Portland cement. European codes don't permit the use of strengths greater than the 28-day value in calculations. In the United Kingdom, compressive stress has traditionally been measured and expressed in terms of 150 mm3 crushing strength at an age of 28 days. Cube strengths may be used for compliance purposes, with the characteristic strengths identified as FCK cube. Concrete will normally be specified in terms of these 28-day characteristic strengths. For example, strength class C35-45 concrete has a characteristic cylinder strength of 35 Newton per millimeter square and a characteristic cube strength of 45 Newton per millimeter square. It is seen from the stress-strain curve for concrete that, although elastic behavior may be assumed for stresses below about 1/3 of the ultimate compressive strength, this relationship is not truly linear. Consequently, it is necessary to define precisely what value is to be taken as the modulus of elasticity, E equal to stress over strain. A number of alternative definitions exist, but the most commonly adopted is E equal to ECM, where ECM is known as the secant or static modulus. This is measured for a particular concrete by means of a static modulus. This is measured for a particular concrete by means of a static test in which a cylinder is loaded to just above 1/3 of the corresponding mean control cube stress FCM cube, or 0.4 mean cylinder strength, and then cycled back to zero stress. This is the secant modulus of elasticity. The dynamic modulus of elasticity, ED, is sometimes referred to since this is much easier to measure in the laboratory, and there is very well-defined relationship between ECM and ED. The standard test is based on determining the resonant frequency of a prison specimen. It is also possible to obtain a good estimate of ED from ultrasonic measuring techniques. which may sometimes be used on site to assess the concrete in an actual structure. It can be seen from Figure C that the value obtained represents the slope of the tangent at zero stress, and ED is therefore higher than ECM. The relationship between the two moduli is often taken as this equation. This equation is sufficiently accurate for normal design purposes. The actual value of E for concrete depends on many factors related to the mix, but a general relationship is considered to exist between the modulus of elasticity and the compressive strength. For steel, we can see the D and E figures. These figures show typical stress-strain curves for hot-rolled high-yield steel and cold-worked high-yield steel. Milled steel behaves as an elastic material, with the strain proportional to the stress up to the yield, at which point there is a sudden increase in strain with no change in stress. After the yield point, this becomes a plastic material and the strain increases rapidly up to the ultimate value. High-yield steel, which is most commonly used for reinforcement, may behave in a similar manner or may, on the other hand, not have such a definite yield point, but may show a more gradual change from elastic to plastic behavior and reduced ductility depending on the manufacturing process. All materials have a similar slope of the elastic region with elastic modulus ES equal to 200 kN per mm square approximately. The specified strength used in design is based on either the yield stress or a specified proof stress. A 0.2% proof stress is defined in Figure D and E by the broken line drawn parallel to the linear part of the stress-strain curve. Now we know the stress-strain relations for reinforced concrete. Next, we will introduce the shrinkage and thermal movement. As concrete hardens, there is a reduction in volume. This shrinkage is liable to cause cracking of the concrete, but it also has the beneficial effect of strengthening the bond between the concrete and the steel reinforcement. Shrinkage begins to take place as soon as the concrete is mixed, and is caused initially by the absorption of the water by the concrete and the aggregate. Further shrinkage is caused by evaporation of the water which rises to the concrete surface. During the setting process, the hydration of the cement causes a great deal of heat to be generated, and as the concrete cools, further shrinkage takes place as a result of thermal conduction. Even after the concrete has hardened, shrinkage continues as drying out persists over many months, and any subsequent wetting and drying can also cause swelling and shrinkage. If the change in volume of the concrete is allowed to take place freely and without restraint, there will be no stress change within the concrete. Restraint of the shrinkage, on the other hand, will cause tensile strength and stresses. The shrinkage stresses caused by reinforcement in an otherwise unrestrained member may be calculated quite simply. The member shown in Figure A has a free shrinkage strain of epsilon Cs if made of plain concrete, but this overall movement is reduced by the inclusion of reinforcement, giving a compressive strain epsilon Sc in the steel and causing an effective tensile strain epsilon Ct the concrete. Thus, we obtain this equation, where Fct is the tensile stress in concrete area AC and Fsc is the compressive stress in steel area AS. Equating forces in the concrete and steel for equilibrium gives this equation. Substituting for Fct in equation epsilon Cs, we obtain this expression. If alpha E equal to Es over ECM, then we can derive the steel stress equation. Now we can use an example to illustrate the stresses in reinforcement and concrete. A member contains 1% reinforcement, and the free shrinkage strain epsilon Cs of the concrete is 200 times 10 power minus 6. For steel, Es equal to 200 kN per mm square, and for concrete, ECM equal to 15 kN per millimeter square. Hence, from the previous equations, we can calculate the stress in reinforcement, which is 35.3 Newton per millimeter square for compression. The stress in concrete is 0.35 Newton per millimeter square for tension. The stresses produced in members free from external restraint are generally small, as in this example, and can be easily withstood both by the steel and the concrete. If the member is fully restrained, then the steel cannot be in compression since epsilon SC equal to 0, and hence FSC equal to 0. In this case, the tensile strain induced in the concrete epsilon CT must be equal to the free shrinkage strain epsilon CS, and the corresponding stress will probably be high enough to cause cracking in immature concrete. Now we continue the previous example to show the calculation of fully restrained shrinkage stresses. The concrete would be given by FCT equal to 3 Newton per millimeter square. For thermal movement, as the coefficients of thermal expansion of steel and concrete, alpha Ts and alpha Tc, are similar, differential movement between the steel and concrete will only be very small and is unlikely to cause cracking. The differential thermal strain due to a temperature change T may be calculated as this equation, and should be added to the shrinkage strain epsilon Cs if significant. However, the overall thermal contraction of concrete is frequently effective in producing the first crack in a restrained member, since the required temperature changes could easily occur overnight in a newly cast member, even with good control of the heat generated during the hydration processes. Now we can use an example to illustrate the thermal shrinkage. Find the fall in temperature required to cause cracking in a restrained member if ultimate tensile strength of the concrete FCT effective, ECM, and alpha Tc equal to alpha Ts. Ultimate tensile strength of concrete epsilon ultimate equal to 125 times 10 power minus 6. Then minimum temperature drop to cause cracking is equal to 12.5 Celsius. Next, we will introduce the creep and durability. Creep is the continuous deformation of a member under sustained load. It is a phenomenon associated with many materials, but it is particularly evident with concrete. The precise behavior of a particular concrete depends on three aggregates and the mix design, as well as the ambient humidity, member cross-section, and age at first loading. But the general pattern is illustrated by considering a member subject to axial compression. For such a member, a typical variation of deformation with the time is shown by the curve in this figure. From this figure, we can see that the final deformation of the member can be 3 to 4 times the short-term elastic deformation. The deformation is roughly proportional to the intensity of loading and to the inverse of the concrete strength. If the load is removed, only the instantaneous elastic deformation will recover. The plastic deformation will not. There is a redistribution of load between the concrete and any steel present. The redistribution of load is caused by the changes in compressive strength being transferred to the reinforcing steel. Thus, the compressive stresses in the steel are increased, so that the steel takes a larger proportion of the load. Concrete structures, properly designed and constructed, are long-lasting and should require little maintenance. The durability of the concrete is influenced by the exposure conditions, the cement type, the concrete quality, the cover to the reinforcement, the width of any cracks. Concrete can be exposed to a wide range of conditions such as the soil, seawater, the icing salts, stored chemicals, or the atmosphere. The severity of the exposure governs the type of concrete mix required and the minimum cover to the reinforcing steel. Whatever the exposure, the concrete mix should be made from impervious and chemically inert aggregates. A dense, well-compacted concrete with a low water-cement ratio is all important, and for some soil conditions, it is advisable to use a sulfate-resisting cement. Air entrainment is usually specified, where it is necessary to cater for repeated freezing and thawing. From conclusions, what we learned: reinforced concrete is a strong, durable building material which can be formed into many varied shapes and sizes. Its utility and versatility are achieved by combining the best features of concrete and steel. The basic properties of concrete and its steel reinforcement include shrinkage and thermal movement, creep, and durability. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I'm happy to answer any questions. Thanks for your watching.